Welcome to our project presentation. Myself Anvesha Dash and my team partner Souvik Dautya is going to present our project for Aero Hub Challenge. Our project topic is analysis and optimization of Boeing 737-100 wing. What is Boeing 737-100 wing? It's nothing but the aircraft manufactured by Boeing company. Then why we have selected Boeing 737-100 wing because its dimensions are available in the internet, and the second reason is that it has no winglet. Having a winglet and curvature on a wing will require a lots of computational power for both the meshing and solving. Here we get the dimension from the internet. This is the diagram of the Boeing 737 wing. This is see my cursor. This is the chord A, this is chord B, and this is chord D. The length of the chord A is 5.71 meter, and the distance between chord A and chord B is 4.83 meter, and the distance between chord A and chord D is 14.18 meter, and the length of the chord D is 1.25 meter. Then we have to find this distance and this distance. In the next slide, we have named this distance as x1, x2, and x3. Now, we have named this total wing for calculation, for easy calculation, that this points is A, B, C, E, F, M, J, K. Okay, and we have divided this wing into two trapezoid. For it will help us to calculate the area easily. So from the triangle ABC, and this is the sweep angle that is denoted as theta1, and this is 25 degree that is given. So from triangle ABC, the tan theta1 according to the geometry rule is the height by base. Okay, so here theta1 is 25 degree, and triangle ABC, the height is BC and the base is AB. So the dimension of the AB will be same as JK, as AB is parallel to JK and they both are perpendicular to AK. So the length of AB is 4.83 meter, and putting the value of AB and tan 25, we will get the value of BC, that is x1, and that we have get 2.252 meter. Similarly, from triangle AEF, tan 25 degree is equals to the height by base height is EF and base is AE. EF we have denoted as x2 and AE is 14.175 meter. Now we get the value of x2, that is 6.6099 meter. Now comes to x3. X3 is a CJ. So BJ, this total length minus BC, then we will get the value of CJ. CJ is x3. So BJ is 5.73, that both are parallel to each other and perpendicular to JK. And the BC is 2.25. And then we get the value of x3, that is CJ, that is 3.46. Next, the projected area calculation. As we have discussed that we have divided the airfoil into two parts. Now you can see that airfoil into two parts, that is A1 and A2, for getting the value of projected area. This area, we will find this area using the trapezoid formula. This length and this length is parallel to each other, and this is the perpendicular distance between these two parallel length. So A1 value is half into cos theta of 4.83 into the summation of these two parallel length, that is 5.71 plus 3.46. Similarly, the value of A2 is, here the parallel length is this 3.46 and this value 1.25, and the perpendicular distance should be like this. So the value of A2 is half into cos theta of 9.345 into 3.46 into the cos beta of 1.25. Then we will get the value of A2. And the total area is A1 plus A2. Here the theta is the dihedral angle and the beta is airfoil derotated angle. What is theta and what is beta? We will discuss later. Now the comes to dihedral angle. Dihedral angle is nothing but the cos component of the airfoil first position. Like when the dihedral is 0°, then we will call this the first position of the airfoil. When it is at rest, then like this airfoil is in rest, and the angle is 0°. Dihedral angle is 0°. Means dihedral is nothing but the angle between two planes. That means the wing and these planes are in same position. So the angle is 0°. So when we will move it to 6°, then you can find the difference between the 0° and 6°. There, this is the 6°. So the dihedral angle is the upward angle from horizontal to wing. You can see that from horizontal to wing. It increases the lateral stability in bank by causing the lower wing to fly at high angle of attack than higher wing. Basically, it's the angle between two planes. Here we keep it as 6°. Now you can see the difference. Next comes to the airfoil derotate angle. What is D? D denote the edge airfoil. You all know that airfoil is the building block of the wing or the aircraft and the aircraft. So this is the edge airfoil. There are so many airfoil in the wing, but this is the edge airfoil. This airfoil is denoted as D. When this airfoil will rotate and makes an angle, then we'll call that is a derotate angle. Now we have keep this edge airfoil as 0°. When we will move it to a certain angle, see the 45°, we have keep the derotate angle as 45°, and says now you can see the difference. Next comes to the angle of attack. Angle of attack basically it's the angle at which relative wind meets an airfoil. This angle formed by chord of the airfoil and the direction of the relative wind. Relative wind direction will be same, but if we'll change the chord of the airfoil to a certain distance direction, like it was like this, now it is like this, it will make an angle 30° with the relative wind direction. This is the angle of attack. And next comes to the translation and motion of the airfoil, changing the sweep of the wing. This is the airfoil. This we have already discussed that this is the airfoil D. It will translate forward and backward, and then it will, depending upon the movement, sweep angle will be changed. Okay, and area will be constant. Like in the first case, we have kept the D translate at 6.601 meter. Earlier we have discussed the D rotate angle, when the edge angle will rotate, but when the edge angle will move backward forward, that will create a translational motion, and will, due to this motion, the sweep angle will change. Remember it. So this is the 6.601 meter. Earlier we have kept. Next we will keep is as 5 meter. Now you can see the difference, but the area will be same. Next, when we will keep is as 9 meter. Now you can see the difference, but area will be also same. Next comes to the main part, that is fluid domain. For solving this solving this, we have keep this total model into a domain, and here the domain scale is scaled down by factor of 100. That means as we keep the chord length at 5.71 meter of the wing, that will become 0.057 meter on this domain. This is done so that meshing can be done on our laptop's computational power. Next comes to the main part of the ANSYS or analysis, that is meshing. So we have kept the meshing, we have selected tetrahedral cell for meshing, and the size of the meshing away from the wing is 20 millimeter, and the size of the meshing by tetrahedral cell near the wing we have kept as 1 millimeter. This is a fine meshing. Now the next part will be described by my team partner Souvik Dautya.
Thank you, Anvesha, for explaining so well the geometry and the meshing part. Now, coming to the solver part, we have used pressure-based solver in a steady state, and we have not used gravity for our simulation. We have used for turbulence modeling, we have used KF-Silent, we have used KF-Silent realizable model, and we have used standard wall functions. Okay, so next, the sizing part. For the sizing part, we have used Reynolds number. So Reynolds number of the real wing equal to the Reynolds number of the model wing. So the reason why Reynolds number is used because it is a non-dimensionalized number, and so here, as we can see, Reynolds number formula, rho u L by viscosity. So the we have not changed here the density or the viscosity of the liquid for the real wing and the model wing. So if it becomes the velocity into the length of the real wing into velocity into length of the model wing. So as Anvesha had said, my teammate Anvesha had said that we have scaled down our model by a factor of 100. So this is 0.01, and so the U2 becomes 100 times U1, which means if 1 meter per second wind flows on the Boeing wing, 100 meter per second should flow on the model wing. So that is what we have taken. We have taken 1 meter per second case on the Boeing wing, which becomes 100 meter per second on our wing. So the Mach number becomes 0.294. And as Mach number 0.294 is less than 0.3, so we have ignored the compressibility sizing of our wing. So next, the CL value, we have calculated the CL and CD value by the formula lift by dynamic pressure into area into drag by dynamic pressure into area. The area was calculated by the formula my teammate Anvesha previously said. So the design point table, here the first, the angle D rotate. The airfoil D rotate. So this is the airfoil D and it is rotating, and we have rotated, this is the extreme case of 45 degree, but we have rotated it to a zero, from 0 degree to 6 degree, and we have seen what changes it brings to the lift and the drag. So these are all the parameters that we have set. These are the input parameters. We have taken airfoil D translate, airfoil D rotate, dihedral angle, angle of attack, and velocity as input parameter, and we have used lift and drag as output parameter. So we are getting lift and drag values from here. So we have calculated, so from the next part we have pasted those values here, and we have calculated the area through the formula, the projected area, which was explained in previous slide, and we have used the CL and CD formula to find the CL and CD, and then we have found the CL by CD for angle D rotate from 0 to 6 degree. And looking at the CL graph, we can see a linear increase in the CL as angle D rotate increases. Now looking at the CL by CD graph, we can also see a linear increase from 0 to 6 degree. So how do we determine which angle is the optimized angle for our wing? So looking at the CD graph, we can see from value 1 to 6, it increases linearly, but from 0 to 1, the value decreases. There might be two reasons behind this. The first reason being that some airfoils have the CD value minimized not at 0 degree, but at some other degree. Maybe it might be 1 degree, it might be -1 degree. For this airfoil, it might be 1 degree. We don't know. Those are Boeing's secrets, and so it might be 1 degree. And the second reason being that our mesh was not that fine, so it might be some error due to not being a very fine mesh. So looking at this graph, we can see that between 0 degree and 2 degree, there is not much change in CD, but there was a significant change in the CL, as we can see here. So we can say here that at a small drag penalty, we get a huge increase in CL. So we have chosen 2 degree as our optimized angle for airfoil D rotate. Now this is design point table 2. So here what we have done, we have taken the 2 degree our optimized angle here for airfoil D rotate, and we have changed the dihedral angle, which was previously just 6 degree. We have changed it from 0 degree to 8 degree to find the optimal dihedral angle. Going to the next slide, we have calculated the lift and drag through ANSYS solver, and we have found the area as explained in the previous slides, and CL by CL and CD. So if we look at the graphs, the CL plot increases linearly from 0 to 2 degree, and then there is not much change between 2 and 3 degree value, and from 4 to 8 degree we see a increase decrease pattern. So if we had to choose, just by looking at the CL graph, if I had to choose the maximized lift, I would choose between 4 degree, 6 degree, and 8 degree. So here the coefficient of lift by drag value. So this graph also increases till 3 degree, and then again there is this increase decrease pattern. So but here between 4 degree and 6 degree, the CL by CD value is maximum, and 8 degree it falls a little bit. So looking at this graph, I would choose between 4 degree and 6 degree the dihedral angle. So going on to the next slide, coefficient of drag, we see an increase till 2 degree, and then there's a decrease of CD at 3 degree. Then there is increase at 4 degree, and at 5, 6, 7 it increases but very slowly. So previously we said that if we had to choose the optimized angle, we have to choose between 4 degree and 6 degree as CL by CD is maximum there. But if we look at the drag plot, the CD is very large for for angle 4, and for 6 degree it's not so much. So between 4 and 6 degree, if I had to choose, we would choose 6 degree for optimization. So here we have taken dihedral angle as 6 degree as optimized dihedral angle for our wing. So here this is design point table 3. Now we have kept the airfoil derotate optimized angle as 2 degree, and we have kept dihedral angle optimized at 6 degree. Now we are changing the translation of the airfoil. These are the values of the translation that we are doing, which changes the sweep from airfoil B to airfoil D from minus 30 degree to positive 30 degree, and an increment of 5 degree each time. This is the sweep of the airfoil. So we have calculated using ANSYS solver the lift and drag values, and we have calculated the area. As my teammate Anvesha said, that area does not change when we change the sweep. So the area is same, and the CL by CD you have calculated, and CL by CD you have calculated using the formulas. And looking at the CL graph, we can see that it increases till minus 20 degree and then decreases for minus 15. And again, if we look from minus 5 to 5 degree, it again increases, the CL increases, and then again decreases at 10 degree, and there is a sharp decrease at 15 degree, and then again it decreases from 20 to 30 degree. So the CL is maximum at 5 degree here. Remember, this is the sweep of the airfoil, so it is maximum at 5 degree, and between 0 and 10 degree there's a little change between the values between 0, 5 and 10. So looking at 0, 5 and 10, we have reached the drag plot. From the drag plot we can see that if we look at the drag plot, it increases till minus 5, then it almost remains same for these three values for minus 5, 0 and 5. Then there is a decrease in drag at 10 degree. So previously we said that if we had to choose between for maximum CL, we would choose between these 3 points, which is 0, 5 and 10 degree. And now we're looking that at 10 degree, the drag is very low compared to 0 and 5. So if I have to choose between these 3 points, I would choose 10 degree sweep angle. Now looking at the CL by CD graph, it is very clear that the maximum CL by CD is reached at 10 degree. So we have chosen the optimized angle as 10 degree. And this is the pressure plot on our wing. So you can see that the pressure on the this here is 25 degree sweep from airfoil A to airfoil B, and from airfoil B to airfoil D, you might think is a forward swept wing, but we have calculated the previous slides that forward swept wing was not the optimized angle. This is 10 degree. If we draw a line here and you measure it, it will be 10 degree sweep. So this is the pressure control on the wing. As you can see, the pressure is less towards the forward of the wing, towards the leading edge of the wing on the top side, as it should be, so that the velocity increases. And if this is a top view of the pressure control on the wing, so the top side, the lowest pressure is on the leading edge, and it increases as it goes to the trailing edge. So the velocity will also increase as pressure decreases. We know that velocity increases, so velocity will be maximum at the leading edge, and then it will decrease towards the trailing edge. And if you look at the bottom view of the airfoil, if you compare the contours, the decrease in pressure is much less in the downside of the wing compared to the top side. So this wing will create lift. So if you look at, this is a very interesting picture. This is streamlines, and we are looking from positive x-axis, which means we are looking from behind the wing, from the outlet we are looking. towards the wing, and you can see that there is this. Let me zoom in this picture. Now you can see that uh, from the um, from the wingtip, there is this pattern of vortices forming. The streamlines are turning uh, as if there is some force turning it, and this is known as wingtip vortices. So this is the thing that you are seeing is wingtip vortices changing the streamlines, and this is the downwash of the wing. So this is the downwash created by the wing, and this is because there is no winglet here, so the downwash is very high. If there were no downwash, suppose this in this domain there were no wing, you would see that, instead of forming this kind of vortices, it will be green dots, which indicates that they are entering and leaving in a straight line. So next, if you look at the velocity streamline vectors, they take the shape of the airfoil and it moves on. This is the video. These are the particles uh, showing the interaction between the air and the wing. As you can see, the top side, the air molecules accelerate and the lower side does not. And this is the phenomenon that creates lift on a wing. You can see that it moves faster than the lower side. You can see that it increases, velocity increases on the top side. Okay, so in conclusion, we can say that the simulation from the simulation results that airfoil lead rotate angle is optimized at 2 degrees and the dihedral angle is optimized at 6 degrees. The sweep angle of the wing from airfoil B to airfoil D seems to be most optimized for 10 degrees. These parameters further need to be optimized for a high speed flows, since we calculated these for 1 meter per second on a Boeing wing, Boeing 737, which has a very high cruise speed. It has, I think, a Mach number of 0.8 at cruise speed. So we need to further calculate for high speed velocities to find the most optimized wing. So these are the some references that we took. That these three references were used for making the airfoil, for getting the airfoil dimensions, and these three were for the airfoil plotting. Thank you very much. That's it.